So, welcome everybody to the colloquium. I'm glad you all made it here and you realize that the colloquium is shifted in time, right? So it's from noon to 1 for the whole semester. So and we'll start out the colloquium actually with an excellent speaker and someone that we know since many years, and we have followed his work, and he's doing amazing stuff with ultracold atoms. That's Professor Giacomo Roati. He is at the Institute of Optics of the Italian National Research Council, that's the CNR-INO, and also at LENS. LENS is the European Laboratory for Nonlinear Spectroscopy in Florence, in Italy. And LENS is actually quite a famous institute. It was found as a European scientific research center, providing advanced laser and spectroscopic facilities for researchers from the European countries and promoting and facilitating the exchange of ideas, scientific techniques, and technical skills. And the senior research staff as LENS consists of professors from the University of Florence, like Giacomo, and other associated universities. And Giacomo is group leader of the strongly correlated Fermi systems lab, and his team does fascinating experiments with ultracold lithium atoms. He got his PhD in physics from the University of Trento. That's another powerhouse in the field of ultracold atoms. And I don't know if you know the book from Stringari and Pitajewski. So Stringari and Pitajewski, they are out in Trento. So it's one of the very famous groups out there too. And he was working on quantum degenerate potassium rubidium mixtures under the supervision of Massimo Inguscio. Massimo Inguscio is yet another one of the very big names for the ultracold atoms. And then until 2005, he was a postdoctoral fellow on experiments with degenerate atomic mixtures at LENS. Then he became researcher and permanent researcher, and now he's got the rank of Director of Research at CNR-INO. He has got a stellar list of publications, and his activity focuses on the study of quantum transport phenomena. So, for example, he has characterized the Anderson localization transition with an ideal Bose-Einstein condensate. That was a big deal, actually observing Anderson localization and tailored disorder potentials. He has done very nice stuff on quantum spin transport in degenerate Fermi gases. And more recently, he has studied the Josephson effects with superfluid, strongly correlated fermions. So, you know, Josephson junctions are, of course, all the rage for the cavity QAD and quantum bits and quantum computation, and the ultracold atoms actually give a very nice platform for studying the physics underlying Josephson junctions. So today he's talking to us about another very famous experiment from this group that was actually published just very recently. It's about a vortex collider, a quantum vortex collider. So we're very happy to have him here, and please welcome Giacomo Roati.
Well, first of all, thank you, Peter, for the very nice introduction, and thank you, Michael and Peter, for the invitation. So I'm very glad to be here, and again, probably next time that we meet will be in person, because I really like to visit your university and your laboratories. So as Peter was saying, today I'm going to talk about our last results in some way that is related to the study of vortex collider, and I will show you how we produce vortices in a quite reproducible and programmable way, in some way using the same idea of this, the very famous, I think that everybody knows about the Rydberg array register. Well, what I'm going to show you is that we can produce an analogy, in analogy to this, the same concept, but using vortices, actually quantum vortices. So before starting, I think that I like to mention the people that really, in fact, participate to the work and in fact carry out the work. And this was the idea of Wujing Kwon, that is postdoc in my group. And then we had Giulia Del Pace, that was a PhD, now is postdoc in the group of Jean-Philippe Brantut in Lausanne. Then Francesco Scazza, now professor at the University of Trieste. And then, okay, these are two young students, master students. In fact, they participate in the last part of my talk. I will give you the outline and the present status. And these two guys really made this last part possible. And we had a collaboration for this work by Claudia Ksani, that is a postdoc in my group, but from the theory side. And then Luca Galantucci, that is, I think now professor as permanent position in Newcastle in the group of Carlo Barenghi. Okay, so when we decided, about this colloquium, I thought that was in any way good to give you some introduction, and this would be, and I apologize if it is then too much, let's say, not basic, it's wrong to say that, but a more general talk, is not technical, but of course I'm very happy then to discuss also some more technical part. So why ultracold matter is interesting? Well, because as you know, we can tune many parameters. And this is very good because from the experimental side, we can tune interaction, we can tune the population, for example, spin population, and we can also play with systems that are attracting or repulsing. And in principle, this can be used also to create a strongly correlated system like the case in which we work. The other point that is very important is that it's possible to tailor optical potential almost arbitrarily. This means that you can create, for example, lattices, you can create disorder, and you can create also some more exotic configuration. But then, of course, what is nice is that you can mix this possible realization in one realization. Since now, and I will enter this later, it is possible to really create a potential with light using spatial light modulator or digital micromirror devices that allow you really to create any pattern that you want. And again, I come from Europe, and probably, but there will be the same in the United States. And now is the second quantum revolution moment in which quantum technology, are playing some important role. And this means the message that I want to convey, of course, that the fact that you can control all the parameters allow you to think about these ultracold atoms like synthetic quantum materials, in which eventually implement quantum computing, in fact, scheme, or, and this is the case of my experiment, quantum simulation experiment. So as you probably have understood from the title, I'm talking about vortices, and vortices are typically related to superfluid or superconducting state. And again, there are maybe students in the audience, and I like from my side always to try to tell the story also of the discovery. And this is what happened in this slide, because this is what Kamerlingh Holmes said in 1913, in this Nobel lecture, after the discovering of superfluidity and superconductivity, in fact. What is nice is that has been said that the experiment left no doubt that as far as accuracy of measurement went, the resistance disappeared. And then he said, thus mercury at, okay, this is the temperature, has entered a new state. And this, in fact, is superconductivity. So as I know, you are very expert both in the experiment and in the theory, of course, on this state. But and so, it's obvious for you that this state, superfluidity or superconductivity, can actually show up in many different systems in nature. You can go, for sure, from liquid helium to superconductors, of course, nuclei, neutron stars. And of course, we know very well that this happens also for gases, so atomic, Bose and Fermi gases. And again, I don't know, maybe this slide is a little bit too much basic, but these are phenomena that in some way can trigger also the interest of kids, and not only of kids. Of course, typically superconductivity and also superfluidity, of course, are related to the absence of viscosity and of resistance, even though I would say probably the more accurate way to define a superconductor is the fact that it is able to expel a magnetic field. But anyway, this is the Meissner effect. But anyway, that for saying is that we can consider this system or this state in which there is no friction, no resistance, no viscosity. Well, from a fundamental point of view, we like to describe this state of matter with an order parameter. And this order parameter is a complex function in which there is an amplitude and a phase. And if you want, what was saying Peter before about the Josephson measurement, I will not touch this in any moment in this talk here. But the Josephson effect, in fact, is the tool that typically people can use in superconductor, and now, of course, also in superfluid, atomic superfluid, to pinpoint the order parameter, because it is able to get information about the modulus of the wave function and the phase of the wave function. And why is important the order parameter? Because the order parameter is a quantity, is a function, if you want, that disclose the intimate and microscopic properties of the condensate or superfluid state. And of course, quantum statistics, in some way like Michelangelo, is able to shape the excitation spectrum that in fact is encoded then in the order parameter. And in some way, this is another side of the coin, because of course, the excitation spectrum tells you how the system is able to resist to the superfluid state against, for example, dissipation. Well, you know that the modulus square of this order parameter is typically associated to the condensate fraction or the superfluid fraction. And this again, I want to be clear, typically when we speak about Josephson dynamics, I like to talk about condensate fraction, but people from helium like to say about superfluid fraction. These two quantities are not exactly the same, and of course are not the same, and also in the number, in the quantity, how much they are very different. For example, if you consider even helium-4, in which you have only 10%, probably a few percent of condensate fraction, while the system below critical temperature is fully superfluid. On the other side, you get that the gradient of phase is due to the velocity of the superfluid. And this is something that will be very important to about what I'm going to tell you later. Well, now, I am an experimentalist, so one can think that this idea is quite, in some way, not real. It's like maybe more conceptual than something that you can really measure. But just to tell to the student that, in fact, the order parameter for a three-dimensional BC, the one that probably you have also, you have all seen, Peter for sure worked with that, is in fact the condensate fraction. And again, the condensate fraction for this system or for this experiment is something that you can really measure, because you do time of flight. And then what you do, you get a profile. And from this profile, in fact, you really get the measurement of the order parameter. Well, going back, in fact, to fermionic system, what, again, just for students, but not only, I think that it is important to really acknowledge the person that allowed many of us to do this work, because she was the pioneer of this field of ultra-cold Fermi system. And she's Debbie Jean, unfortunately passed away a few years ago. And again, this sentence is quite interesting, because she was presenting, I think, to the journalists, the physical regulators, in which they were observing for the first time the fermionic condensate. And in fact, she said that this is a new form of matter related to Bose-Einstein condensate and related to superconductivity. But this system, the fermionic condensate, is not a Bose-Einstein condensate and not a superconductor, but it is really something new that in some way link these two behaviors. So that is what, in fact, we study in my laboratory, and not, of course, there are many other laboratories in the world in which people study BEC-BCS crossover. And this is why, it's interesting, because in some way you find something that can be connected to maybe typical Bose-Einstein condensate or typical BCS superconductor, but it's something new, it's something different. And again, this is probably, all this phase diagram that was in fact presented by Randeria in 2010. Here we present, I am presenting, the interaction parameter 1 over kf, where kf is the Fermi wave vector, A is the S-wave scattering light that I can tune. This is the temperature. And you see this yellow area is where the superfluid or the condensate state exists. And in this direction, you get approaching, never approach in the real experiment in the ultra-cold gases because the critical temperature will be too low, the BCS state, while in this direction, you get the BC state. And what happens when the Feshbach resonances, you are pinpointed the center of the Feshbach resonances, so you are infinite scattering length, so this interaction parameter is going to 0, you get the so-called unitary superfluid that Michael and co-workers work with that a lot. So this system is very exotic, is super strongly correlated, and typically per size is of the size of the order of the mean interparticle spacing. So again, this probably is a slide that is too much maybe straightforward for many of you, but this is just a Feshbach resonances, and apply a magnetic field with a pair of coils, and with the Feshbach resonances, with this way, I can tune the scattering length. In particular, and this I will enter in some detail later, between two spin state of lithium atoms, okay? Well, if you are in a regime for which the scattering length is positive, well, what happens is that this is the two-body scattering problem, exists a molecular bound state. That means that if you lower the temperature of the system enough, then it's very probable that you form molecules by three-body recombination processes. And the system at the end, and there are many reasons for which this happens, and I will not have any time to tell you, but the system is anyway stable, and the system then forms molecules that are bosons, and then the boson can condense to Bose-Einstein condensate. On the other side, on the negative side, of course, in principle, will be a negative side, but with very small negative interaction. But of course, this again will not happen because temperature will be too low for accessing the superfluid state. Anyway, for the negative side, there is no any bound state in the two-body problem, but still atoms can in some way pair using many body processes, and these are a sort of Cooper pair-like, I mean, if you want. And this again is the so-called BCS limit of superfluidity. Again, in the center, so where the scattering length, in fact, is from mathematical point of view infinite, but that's say meaning that the scattering length is giving you the maximum cross-section possible, that is 1/k², in fact. Well, there does not exist any bound state, and the system anyway still pair in this unitary superfluid that has very special properties. So how is possible to probe this quantum state or the quantum nature of this state? And again, as you see from my slide, I put two properties that in some way people typically like to mix. And for example, for Bose-Einstein condensate, very dilute at =0 in some way are different in the definition, but are equal in the quantity that, I mean, everything is condensate and everything is superfluid. But I would like to keep some distinction. Well, the condensation is probed by, for example, for sure by the Josephson effect. And here I just show a superconducting Josephson junction, our gas superfluid, the Fermi superfluid, the Josephson junction, and this is the work by the Henning-Moritz group in Hamburg, in which it was still using a Fermi superfluid, but in 2D. Then, of course, and this will be the last part of my talk, so I spoil a little bit. You can study something that gives you indication, and this, for me, still I have to create some idea in my mind that is very definitive. Maybe some support from you would be nice. If you study persistent current, for example, in a ring, then of course you can access to something that is for sure related to the superfluid state, but still I'm wondering if it's also connected to something that is peculiar of the condensate state. And this again is a superconducting ring, and this is the ring that we have now in my laboratory with Fermi superfluid, and we are doing some physics with that. On the other side, superfluidity is typically associated to the presence of superconductivity, the presence of lattices, of vortex lattices. And again, this is an example of Martinsville experiment in MIT with Fermi system, and this is a typical, I don't know if it is typical, but it's a superconducting vortex lattice, or vortex lattice in a superconductor, if you want. Of course, created by the presence of a magnetic field. Well, again, I'd like to say another sentence given by another Nobel Prize, Eric Cornell. Typically, vortices are really considered like the heart of the superfluid state. And he says that anytime you think about superfluidity, you have to think about vortices. Okay, so that is more or less a long introduction that anyway put in the framework to start what in fact is the work carried out in my laboratory. The first point that I want to mention is that naturally vortices are not quantum objects only, but naturally you can see in many systems, even in the classical description in the world in which we live. This, for example, is a hurricane. And so these are classical systems, classical vortices. Of course, on the other side, you can find in quantum fluids. This again is the Martin-Swirling experiment in MIT. So how can I distinguish this? Well, I distinguish this if I just define the circulation. That is this quantity, so is the velocity field integrated along a closed path. Because in the classical system, gamma can assume any value. And it is pretty simple using the definition of the velocity given by the gradient of phase. It is pretty simple then to see that for quantum vortices, gamma cannot be assume any value, but must be quantized. Okay, and that again, this is given by just using the relation that I was mentioning before. So, and the question is that how a vortex in general, how can dissipate energy? Well, in the case of a classical vortices, this is possible in a very easy way using the viscous friction. So in some way, vortices, classical vortices, smoothly lose energy by viscosity. Well, the point is that the first issue is that when you consider a superfluid at equal 0, suppose where you don't have any normal component, for example, then you can have a problem because, of course, the viscosity of a superfluid tends to be 0. So how is it possible that vortices can dissipate energy? Well, again, I will not enter any detail, these are formula, but just to tell you that the vortex can lose energy because even there is no friction, then quantum fluids and typical BC, of course, and also unitary system is the same with a different value, but are all compressible. So in some way, you know that you can find phonons, and this you know very well. I mean, in the laboratory that Peter is carrying out. I mean, the Faraday wave is a typical pattern of sound, so it's possible to have sound. So this decomposition of the kinetic energy will tell you that it's possible then to see how vortices and possibly sound are connected, because in some way, and this is at this point is just a speculation, and then we see if it then becomes true in the experiment. If vortex can lose energy, transferring incompressible energy of the swirling flow to a compressible degree of freedom, if you want, that are phonons in the system. Well, this is in some way possible, at least in the theory, for sure. You know, there are many examples, and again, Michael is an expert in this. I mean, with Ariel Bulgak, I mean, did also some work on this. So about quantum turbulence, you know very well that the vortex can recombine, vortex line, and then in the recombination, there is the possibility absolutely of vortex, that vortex lose energy in sound. And again, this is another experiment that is not related to cold gases, but you see that in 2D in particular, accelerating vortices can be thought like accelerating particles. And you know that typically this should emit and lose energy. And in this case, lose energy, meaning lose energy via sound emission. This is an example of a plasma experiment. Well, then, of course, we can think about the fact that maybe exists also the possibility that vortices can lose energy, because maybe you are not at T equals 0, or for example, even if you are at T equals 0 and you consider a Fermi system like at unitarity, the condensate fraction is not 100%, so you have no condensed fraction that is different from 0. And so you can think that it's possible for the vortex in some way to lose energy using the normal part. And here, again, I just mentioned finite temperature effect, but just to be clear, this can happen also for T equals 0 in a situation for which, for example, you have a system in which the condensate fraction is not 100%. But for the moment, just consider this like finite temperature effect. And this was measured in the theory by the group of Nick Prokakis in this paper, in which they were observing how the vortex was losing energy, and this is a coefficient that I'm going to introduce to you later, changing the temperature of the gas. And this is just the precession frequency of the vortex leaving the trap. And you see that this change, changing the temperature. Another point is that, of course, when you consider the physics of many vortices, and this in the group of Shin in Seoul, it is possible that also in this case, the mutual friction that can be between vortex and normal part change also the way in which more vortices interact between themselves. Because change in some way can change the separation between this, for example, is a vortex dipole, in which it changes the distance, changing the energy. Okay, the concept of that I'm describing you is not something that is only related, in fact, to cold gas. It actually is not for all, because this is our concept that are very well known in the concept of superfluid helium, for example, and with some difference, I would say also in superconductors. The only thing that would change is that in the case of superconductor, you have a Lorentz force acting on vortices that, of course, in this case, in the case of, for example, helium or a neutral system, you don't have. But anyway, you can consider that the mutual friction, you want to consider like a force that is phenomenologically introduced in the problem to take into account possible dissipation mechanism at finite temperature. So the mutual friction, okay, the relation is this one. I will not enter any detail, it's not important, but just you have to think that is related to the presence of a normal state that has a velocity. This is the velocity of the vortex, and in some way tends to slow down or to create a mechanism for the vortex to lose energy with some coefficient, gamma or alpha, like I'm going to tell you later. On the other side, the fact that the vortex is moving in a superfluid anyway gives another force that is the Magnus force that in some way is proportional to the superfluid density. Both the forces must be included to consider the dynamics of the vortex. Well, there are experiments, and these are experiments, for example, two experiments done in helium-4 and helium-3. So this quantity are, you have to read the paper, but just to tell you, are effective viscosity term. And what they do in the helium-4 is to change the temperature, and what they see is that, of course, this effect decrease, because again, you are decreasing the possible normal component or non-superfluid, in this case, component or non-condensate component of the superfluid in using the temperature in both cases. But what is important to show is that you see that this quantity, so the viscosity, the final viscosity that you get in both experiments does not reach 0. So what happened? That you can have then two mechanisms that now in principle are responsible for the losing energy of the vortex. One is the mutual friction that we can consider like exchange of momentum between vortex and non-condenser, or between vortex and quasi-particle, for example, in the system. And then there is another term that is the interaction or the production of sound, that in principle this is can be considered like the last or the limiting effect that happens even at equal 0. Okay, so typically this can be hard to disentangle. And I would say for sure in ultracold system, the sound emission produced by vortex dynamics was never measured. And then the question that of course we want to answer is this: is possible to study this phenomenology in the BEC-BCS crossover? Because of course you can expect in some way that the different kind of superfluid state can eventually change the way in which vortex lose energy. So I do apologize, probably this is the longest introduction that you ever had, but of course the last, will not be so long, but it's just to give you really a motivation for why we study this. So this is the summary. If you want, we produce, I will tell you how we work and produce homogeneous quasi-two-dimensional Fermi superfluid. And then I will enter in the topic. So I will tell you how we can program our system to produce vortex on demand. And I will tell you how we study collision and annihilation processes of quantum vortices. And then I will give you just some hint that maybe can be useful for next discussion, maybe about persistent current in Fermi superfluids. So, as Peter was saying, I work with lithium. So this is probably the only experimental part about lithium that I'm saying you. So we use flashback resonances in the two lowest hyperfine state of lithium-6. And in this way, we can produce and we can study the BEC-BCS crossover. So the thing that we can do in our lab, and there are many labs now that can do the same, is to shape potential using DMD. And the DMD can produce any pattern, and this pattern then is imaged actually on the system, on the Fermi system, with high resolution through a numeric, I would say high is not high, is super high, but it's quite high anyway, numerical aperture microscope objective. And this is an example of the DMD that probably you know. Of course, we can produce anything that we want. And I'm very proud to show the skyline of Florence reproduced on our Fermi superfluid. So that is what we have. These are the ingredients, in fact. So we produce a single layer. And of course, now you know 2D system, Bose and Fermi, but okay, in the case of Fermi are a very hot topic, and there are many laboratories. Of course, this probably I just cite some of them, but there are probably others. And we think that these are nice systems because, of course, are homogeneous in our case, also 2D. So these are considered like a nice playground to study quantum transport on the superfluid, but also in the spin state. And we produce this using a TM01 beam. So we squeeze our Fermi system. And then using the combination of the repulsive imaginary frequency of the TM01 and the real frequency of the residual curvature of the flashback coils, we produce almost flat system. And this is an example. Okay, so this is our profile. And just, because Julia liked round, we produce a round biscuit that is nowadays around the Fermi superfluid in almost 2D. So why we decided to study a collider? So what is a collider? Because, okay, this is, I think that this is an interesting point because you know that typically there are many kind of experiment in which if you want to see what is inside or if there are other particles, of course, you want to destroy what you have and see the final product. And that means that collision can really be interesting to reveal properties that are not apparent of a system or in general of, yes, a system. And okay, there are many cases in which this happens. Of course, this is very famous, but also this is also very famous because this young kid wants, of course, to see what is inside, and the only way to see is to crash and to collide the stick with the horse. But now coming more seriously, why we wanted to study this? Because the production of something that is reproducible, to have an experiment that is able always to start with the same initial condition, is very important. Because in our case, we wanted to create a situation in which to study intimate dissipation mechanism was possible and was in some way easy. And again, what we want to do is to study this for different superfluid state, in some way crossing the helium, the liquid helium to superconductors. And this again is the point that I was telling you at the beginning, because the idea was to create a minimum scalable and programmable platform, exactly like the atomic optical tweezer arrays. But in this case, to investigate vortex dynamics. So I would say the change of paradigm that I want to try to convey you is that our system, while, for example, in the array, the single element, the minimum element is a Rydberg atom, in my case here is a singular vortex, okay? And meaning that if I can do that, then I can assemble as one by one vortex and add one by one vortexes in the system. And then this will be very nice because then I could approach different many body physics, but with vortices. So vortices are my minimum ingredient, one vortex if you want, for to start my experiment. Okay, how this is done? In fact, this was done using a concept that was in part, I mean, developed by Brian Anderson in Arizona, that is to use the so-called chopstick method. So what I do in the experiment is using DMD. So this is my system. And I will just, unfortunately, it's difficult to, I cannot show by my hand, but you just take two beams here, and then these are superimposed at =0, and then you move with finite velocity with an angle, okay, in the superfluid. So as you will see, I mean, if you overcome a critical velocity, then you will pin vortices around the two chopstick beam. So this is the chopstick beam in situ. And after, you see in time of flight, after that the chopstick beam are switched off gradually, of course, you see vortices appearing. Well, I can tell you which kind of vortices are these. Of course, since you don't transfer any angular momentum, but just linear momentum, this can be only a vortex dipole. So it can be vortex, anti-vortex. And the nice thing is that the vortex, anti-vortex is something that is a self-propelled object. And you can see here, we produce, sorry, maybe I will do something. So we start, this is the 0 time. And then we leave the dipole propagates, and you can see that it bounces against the container, and then we'll just perform the same behavior. Okay, this probably, I don't want to enter too much in the detail about the phase that you can do, the angle, but what is important is this one. And if you want also this picture, in which we can see that we can produce with a fidelity of almost 100% a vortex dipole if we overcome a critical velocity. But at the same time, we can produce with some good reproducibility vortex dipole with different size. And this was something that, you know, when you got a good student, actually a good postdoc like Eugene, I learned something that I didn't know, because I was completely ignorant about the vortex dipole, is that vortex dipole is a very nice object because its size, the distance between plus minus, if you want, is just related to the momentum. And the energy is just proportional to the logarithm of the distance, of the size. And as you know, I mean, in physics, you want to do two kinds of measurement. The first is frequency, because you can access very, very, very high accuracy. And the second is a distance, meaning that if I'm able to measure the distance, then I measure everything of this side of this object. Okay, so the first experiment that we performed was quite simple. We produce a vortex dipole with some velocity, and then we let move in a part of the cloud. And then we were looking how the distance could change eventually due to dissipation. So reducing energy means the vortex dipole should become closer. So reducing size, reducing d, meaning that from this measurement, we can extract the mutual friction coefficient. And what we do, we are very far from any annihilation. So of course, you can say to me, okay, if I put this very close to this, then we'll annihilate. And maybe this will be the case. But then we started from a situation for which this size is sufficiently large that this annihilation is improbable, but still we can see the effect of the shrinking. These are the data. And from the data, in fact, what we do, the data measure the distance versus time. These are three regimes, this BC, unitary, and this BCS. And then you can say to me, why you start from a BCS that is such larger than the other two? Because if I produce, and this again is something that someone actually should calculate, because this dynamics is not calculated by anybody. Actually, I know that Gabriel Vaslowski is working in that in Warsaw. But there is no theory on this. So we had to produce a such large vortex dipole in the BCS, because if I produce shorter, then we will annihilate. Let's say that there is, even from this very basic measurement, even the 0 point, so the t equals 0 point, there is a difference. But then what we see is that the size of this change. And as you can also see, the size, the shape, the change of distance in the BCS is much higher. Of course, the only thing that we can try to do, because again, there are no many other tools, at least in the BCS and in unitary, we can use a very simplified model that is called point vortex model, in which we add a dissipative term that is just included in this alpha, that is the mutual friction coefficient. And these are the quantity. Okay, we work typically with winding 1, but of course we can produce winding number much also higher. So from this model and fitting the data, we extract alpha. And these are the regimes of superfluidity. So this is the BC, this is unitary, and this is BCS. Okay, so this is 1 over KF. And you can see we have the behavior change. And in particular, what we do see a change in the behavior in the dissipation. Just look this dotted one, for example, because these are different realizations, but this is not important. We can see that the alpha coefficient increase moving from BC to the BCS. And again, we had discussion with Michael and with Piotr, Andrea, and Gabriel, why in the BCS things should be different. And this is only the first time that I mentioned this, and you will see this also at the end. There will be another slide very similar to this. So what happened in the BCS is that anyway, vortex are different in the sense that they're not dark as in the BEC, because they are like gray, if you want, due to the presence of quasi-particle bound state that are called the underbound state, in which quasi-particle, in fact, can be present. And this effect, this complex structure of the vortex core, can eventually affect even the dissipation in the BCS superfluids. So in some way, we see an additional friction that is not present in the BC. But still, I want to say to you, I mean, this at the moment, our speculation, I would say, are more the speculation, but we did not measure, in fact, this bound state. What we want to do, and this was something that we discussed with Gabriel, is to do the same measurement in the BCS on unitary, changing temperature, because changing temperature, of course, would change, and in some way we could get some indication of the structure of the vortex core. Then, of course, since we can produce one vortex dipole, we can produce even two vortex dipole just using two chopsticks. Actually, 4 chopsticks, but let's call 2 chopstick direction. And this, of course, you can realize from the symmetry of the problem that if I create the system in this way, vortex, anti-vortex, this will be anti-vortex and vortex, for example. And then what happened? Okay, you can launch them against each other. And then I give you the hint. What is happening is that they change pattern. So this vortex pick up the anti-vortex of the other pair, and the other way around for the other two. Can we see this? Yes, we can. And this is an example of collision, 1, 2, 3, 4, and then they collide. And exactly what we see in the trajectory, we see, in fact, the same dynamics that we expect. At this measurement, were done 4 large dipoles. And again, we wanted to avoid any additional mechanism, like, for example, annihilation. And this is an example, is an experimental data. So you can really see vortex, anti-vortex, anti-vortex, vortex, and then this is the region, I mean, they start to collide and then they change partner. Well, of course, what we can do is to try to force or to see the effect of dissipation in the collision. And nicely we can do, I mean, again, this is just a test, but you can, if you see the paper, we can create almost all the possible configuration. This is a head-on collision. This is with a 120-degree collision. So 1, 2 against 3, 4 here. And this configuration is particularly interesting because they increase quite a bit the effect of exchange of momentum between and dissipation, if you want, between the vortex pair. But then we came out with some indication or something, some measurable quantity that can give us indication about dissipation. And as you can see, probably you can see that one idea could be, why don't we compare this distance with, for example, this distance with this distance? Because if this distance, actually, if this distance change with respect to the initial size, mean, for example, is shrinking, means that the vortex dipole is losing collision, is losing energy during the collision, or I mean, in the process of collision. And exactly, sorry, the gamma is not the circulation, is okay, dissipation in this case. And this is an example. This is the BC. So I have to explain you the data. So this is exactly this quantity. The part below, maybe actually you can for the moment not look too much, but this is the probability of annihilation. We are changing the initial size in healing length, very normalized, of the vortex dipole. So just to tell, the point vortex model is this dotted line. This is Gross-Pytajewski. And again, pay attention that Gross-Pytajewski cannot really, without any dissipative term. And you say, why do you do this? Because then, of course, you expect this will not work. Okay, we did not put any dissipation. The fact that the data are in some agreement with the experiment. So the theory data are this shadow, are in agreement with this data set. It's just because the dissipation is super small. Anyway, the data, you can see the yellow are the 100, the head-on collision, and the light pink, I would say, is the 120 collision, 20-degree collision. As you can see, changing the size of the vortex, then you see something happening. So for sure, the point vortex model will not capture anything. And then second, the vortex, the dissipation encoded in this quantity increase. After a critical point, we don't see any more vortex. So the final state is the absence of vortices. So the system annihilates. By the way, sorry, because what is interesting is this, of course, is just a calculation. This is the increase of compressible energy, kinetic energy in the system. Remember what I was saying you at the beginning. So the vortex can transfer the incompressible kinetic energy of the swirling flow to the compressible kinetic part, that is sound. And in the theory, these are simulation, you see that decreasing the size, you expect an increase, of course, in this compressible energy. That means in principle, you expect to produce many phonons. Of course, here we don't know what happens, but we will see at the end. Naturally, we did all this measurement for all the regimes. So we study, this is the BC you have just seen, this is unitary, and this is BCS. Of course, for these two regimes, there is no way for us to do any theory. So this is Michael just a hint for you, because we just use the point vortex model, and this is, I mean, for sure is very qualitative. So as you see, in all the two regimes, there is an increase of dissipation with some high probability of annihilation for quite small dipole. So here I have to renormalize in 1/kf, but still just to tell you, because of course you can be discouraged by the change, this quantity here corresponds to a vortex dipole that is very large, much larger than what happened in the BC. Just to say that in unitary and in BCS superfluid, annihilation or dissipation is much higher, and higher also for larger dipoles, where for the BC the system will not dissipate. And you clearly see that passing from unitary and BCS, you just see from the slope, dissipation quite increase. And again, our point is due, even in the collision between vortex dipole, this is due to the fact that the vortex core has a different nature going from BC to, for sure, BCS, superfluid. So there is an effect of this in the system. And again, this is just speculation, but we can speculate that this can be the case. Well, now come to the point that we see that if we can work with a system with large dipoles, in the BC, we don't see any annihilation. In the BCS unitary, we can always see some more dissipation, but of course, if we work with large dipoles, we see dissipation, but we still can live without any annihilation. Well, it's possible for me to study instead really the production of sound. Well, what we did was to create a vortex dipole pair created at sufficiently short distance. Okay, of course, not too much that they will self-annihilate between them. Pair, the plus and the minus, or 1, 2, or vortex anti-vortex, but that during the collision, they could annihilate. And this is what we did. This is the BC case, for example. These are vortex dipole pair. They are launched one against the other. And then you can see that probably you see on the screen, they disappear, and there is a sound wave, like the wave in a lake when you throw a stone. And the one, of course, up gray are the experiment, and the one below, in this case, are the Gross-Pitaevsky simulation. The agreement, I would say, is pretty fair, is good. And you can see very strange, structure happening. There are rarefaction pulses. I have to still also learn about that. But anyway, the message that I want to convey is that you can clearly see the annihilation and the production of sound by the annihilation of vortex pair, dipole pairs. We can see the same mechanism, I want to say, in the BCS and the unitary. But I want to be very clear, that mechanism is quite more complicated to be seen. Also visually, it's more complicated. So, but this said, we clearly see the effect, because in some collision, we do not see any vortex away, happening out of the collision. So this, I'm coming to the end, so do not worry. So just to slide, what we have now, we have the same system, and we create a ring, and we imprint with the DMD and the objective on the atoms. And then, of course, this is the way in which we produce a ring. Okay, this is the analogous of a superconducting ring done by Fermi system. And this is the way in which we produce it more sophisticatedly. We must use some barrier to avoid any initial velocity on the atom. So this, in fact, is a ring homogeneous, stationary. I will not enter too much the detail of this because I don't want to take all your time, but what is interesting now, we can produce, I'm sorry, this is not the best picture, but we can produce now ring as thin as, actually this is even larger than what we can do, around 2 micron. That becomes very interesting because it becomes size of the ring comparable with the size of the Cooper pairs in the BCS state. And there are things that are very interesting, this one-dimensional, more or less, topology. What we do? Well, since we have the DMD, the first thing that we can do is to try to phase imprint. So to do exactly what a magnetic vector is doing on a superconducting ring. So we can use to imprint it a phase on the superfluid. And in particular, what we do, we use a very strange geometry, and you will see why. We have a ring, and then we have a central disk that will be used like a reference for phase. And we phase imprint only in the external ring using a gradient of light that becomes, for some time of pulses and for some intensity, a gradient of phase. Okay, a phase imprinted to the wave function of the superfluid. And this again is a reference that is used like a homodyne detecting scheme to see if we have an imprinted current. Sorry, phase that corresponds to a current. So when we do time of flight, then we can, this is something that was realized in the group of Bill Phillips and Jean Dalibard. So this is just for Fermi system. But we see that if we don't imprint any phase, we let expand the ring and the reference, we have concentric pattern. But then if we start to do a phase imprinting, we can see spiral happening. And from the number of spiral, we can extract the circulation that we imprint. So winding number 1, 2, 3, 4, 5, and so on. And nicely, counting this means to count, counting the spiral means really to become like a method that we have in our Fermi system corresponding to an amperometer. Okay, typically it's very difficult to measure current in Fermi system or in system, atomic system. Well, this I would say is a very powerful way. And nicely, we can recalibrate everything in phase, and this is the winding number. We exactly see the quantization of circulation that you have to compare with the trapped flux quantization in the case of a superconducting ring. Okay, these two are completely the same kind of physics. I mean, the description, of course, are different systems, but the picture behind is absolutely the same. Well, this is the end. What do we want to do? The first thing that we want to do in the case of vortex dipole and in the case of the vortex collider, we want to study vortex in the presence of binary disorder, to study pinning and unpinning mechanism. And this, again, we had discussion with Gabriel and with Michael. This is very similar to what happened in the superconductors, in which you have a transition between vortex glass and vortex liquid. And of course, this changed quite a bit the property of the system. And now, just since Peter is here, I was discussing with my new PhD that is coming from the group of Jorge Amin in Aurutinian in Mexico City. I mean, he's the guy that did the Faraday pattern in the Fermi superfluid. And I was discussing just yesterday what happened if I pin vortex dipole and then I excite a standing wave or a shock wave, and to see if it is possible to unpin, or which is the possible interaction between vortex dipole and sound. So that is something that we want to study, for example. And now the fact that we can really produce one vortex dipole and we can pin probably with some disorder potential, this will be great possibility to study this phenomenon. On the other side, I mean, we are running also experiment now with persistent current in the rings, and this, okay, is also from the point of view of Fermi superfluid is quite new. There is a work by the group of Wright in the United States, by the way. I know that at least there is an archive paper in which they were showing some ring geometry in Fermi superfluid, but still we are, at least that I know, the only two groups working in this, and the physics that we can do is absolutely insane, because for example, Josephson dynamics between two coupled ring concentric, for example, or to study, for example, what Giamarchi called Josephson drag, that is the friend of the Coulomb drag, I mean, between two rings, would be possible. I mean, there are many things that we can be studying in this geometry. And with this, I want to thank you a lot for the attention. And this is okay, my city. And in case someone wants to do some visit, even short visit, postdoc, of course, it's very welcome. Thank you so much.